Welcome to Wireless Future. I'm Emil Björnsson, and as always, I'm here with Eric Larsson. Are you there?
Oh yes. Hi Emil, how are you this morning?
I'm great. So it's great to be back with another episode, and today I was thinking that we're going to talk about NOMA, or Non-Orthogonal Multiple Access. So if you look back a few years when people were talking about different technologies that will be coming for 5G, for example, then NOMA was one of the things that was talked about maybe the most in the beginning. And nowadays, people are not talking so much about it anymore. So I was thinking that we should take the opportunity to spend an entire episode talking about NOMA. So, as I said, NOMA stands for Non-Orthogonal Multiple Access. So let's break down that name. What is multiple access?
So multiple access, in wireless we always have a shared medium, right? Mm-hmm. We have some chunk of this time frequency domain where we gonna, say, fit all communication links together. And traditional ways of doing that is to slice this time frequency domain in various ways. For example, we slice it in along the frequency axis, then we get frequency division multiple access. We slice it along the time axis, and then we get time division multiple access, and so forth. In the last 20 years, there's also been the development of spatial division multiple access, where the idea is that we have a base station with multiple antennas and it can kind of sectorize the world, right, or look into specific directions so that the same portion of the time frequency domain can be reused at multiple locations in the same cell or in a cell served by the same base station.
I see. So we really need to divide our resources between our many users in these different ways.
Yeah, so also in this context there is CDMA, right? Code division multiple access, where the idea is that you reuse time and frequency universally, or at least within a cell, and then you assign each user a unique code, and these codes are designed such that they are orthogonal in the sense of having zero cross correlation, so that users can transmit the data multiplied by their own unique code, and then just send that product off on the air interface, and the base station despreads by multiplying by the corresponding codes and achieve interference-free decoding. So time division, frequency division, code division, and spatial division. These are like the classical multiple access techniques.
Yes, and if I got it right, then the first generation of wireless standards or cellular standards were based on frequency and time division. Then 3G tried out code division, and then now we are back at time and frequency division and adding spatial division on top of that. Is that right?
That's right. That's a good summary, yeah.
So then non-orthogonal, what does that mean in this context?
So non-orthogonal multiple access means that we let transmissions interfere on the same degree of freedom, right? So either in the same portion of the time frequency domain or in the code domain, such that users use spreading codes that aren't perfectly orthogonal, so that they interfere. So for example, on uplink, that the base station will see a superposition on a sample or on a symbol by symbol basis, see a superposition of signals that were sent by more than one terminal. And correspondingly on the downlink, that the base station transmits at each point in the frequency domain something which is intended for more than one terminal at the same time. So that's what non-orthogonal means.
I see. So then they are sort of interfering with each other. And I would say that if I have two students that start to talk and ask questions at the same time, then I would tell them to please take turns. But why would you benefit from actually letting both talk at the same time?
Yeah. No, that's a good question. And this all goes back to, say, fundamental information theory for the multiple access and for the broadcast channel. So, for the multi-user case, right, where it's known to be better in general to have users talk at the same time and resolve the interference rather than orthogonalize them in time or frequency. And conversely, when transmitting to two users, it's better to use a form of superposition coding rather than splitting the time or splitting the frequency.
I see. So then we have talked about multiple access and non-orthogonal. So if you put them together into non-orthogonal multiple access, or NOMA, what does that stand for? Is it just a combination of these two things?
Yeah, NOMA means, as the name suggests, right, the multiple access schemes that exploits or suffers from, depending on how you view it, non-orthogonality. And in a way, the word NOMA, I think, is a bit of a misnomer because it can refer to many different things at the same time. A lot of folks, when I say folks, I really mean researchers and engineers in communication theory, right? Refer to NOMA. When I say NOMA, I mean power domain NOMA. So really, would used to be like classical superposition coding for the broadcast channel in communication or in information theory. But NOMA can also mean other things, even the fact that you let sometimes users collide. Well, obviously, if you let collisions happen, then you allow for non-orthogonality at that very moment, right?
Okay, so then I was thinking that we structure our conversation to go through these different non-orthogonal schemes that people have been talking about when it comes to 5G, and let's start then with power domain NOMA. Can you explain more in detail what people have in mind to utilize in that case?
It's a power domain NOMA, which is again like the main strand of NOMA, or like the default meaning of the word, right? In principle, it simply means that, let's talk about just single antenna transmitter, single antenna receiver. So the classical multi-user downlink or broadcast channel in information theory, right? So NOMA that means that instead of splitting the time, let's say between two receiving terminals, then we transmit to both of them during the entire time. But when we transmit, we send a superposition of data intended for the first terminal and destined to the second terminal. And then we hope that, or rely on the fact or the assumption that these terminals have different signal-to-noise ratios. Receive the signals we receive the transmission with different SNR, so that one of the terminals can decode both streams and retain only the one that it is interested in, and the other terminal treats one of the streams as interference and is still able to decode its own stream. And this is superposition coding from information theory. It's known to be the optimal way of achieving the capacity region for the downlink multiple access channel. And in principle, power domain NOMA is nothing more than that. It's a form of superposition coding where you send a sum of two signals simultaneously, these two signals being destined to two different terminals. And then you rely on advanced decoding schemes to help the terminals make sense of the transmission.
I see. So it's a bit like recording an audio where two people are talking, and then you figure out what one person said, subtract that, and then you can listen to what is remaining in the recording.
Yeah, it is like that. Yeah.
So it sounds like we need then more advanced algorithms. So I remember a time when I was a PhD student, I was trying to focus on making the handset use as simple algorithms as possible to minimize the amount of processing that needs to be done. And now it's like we are trying to squeeze out more performance by adding more algorithms while with implementations at the users. So do we need this? Is this the optimal way of operating the system?
So that's a good point. It is absolutely true that with the example I gave, the terminals will have to use more sophisticated decoding algorithms as compared to the case with orthogonal access, right? Specifically, they can use a technique known as successive interference cancellation, which is essentially that they listen to a superposition of two data streams and decode one of them, treating the other as additive noise. And then once they have decoded the first stream, they subtract it off from the received data, and then they can decode the second stream. And this is information theoretically optimal if you have like infinitely long data blocks. But in practice, this is a process which is, well, number one, it does take some computational effort, right? But more importantly, it is prone to error propagation. Just to make a tiny mistake in the decoding of the first stream, then you're gonna screw up the second stream and garble that and decode nothing in the end. So it works really best under rather idealized assumptions like infinite block length, and also you need high quality channel state information to do this, and channel state information turns out often to be a limiting factor in wireless communication. So once you consider, all these practical, say, impairments, then the superposition in the form of power domain NOMA just isn't as good as it seemed at the surface.
But this information theoretic optimality, do I understand correctly that this is when you have a single antenna at the base station and, say, 2 users?
That's right. We're talking about a single antenna case here.
And in 5G, there's also talk about having multiple antennas, massive MIMO, these type of things. So if we put multiple antennas into the picture, is NOMA still a optimal scheme?
Hardly. Once you have multiple antennas, then you add spatial degrees of freedom to the system, and that changes the picture quite fundamentally. And as it turns out, you can find like niche cases where NOMA adds a little bit of potential performance. But in general, once you have multiple antennas, the use of NOMA offers very little extra advantage.
Yeah, this is my impression as well, that since there were a lot of talk about NOMA in the discussions that was leading up to the 5G standardization, also companies were trying out these type of things, and when they added it on top of massive MIMO things that are there now in 5G, the gains were not convincing enough. So at least so far, there is no features of NOMA in the 5G standards.
No, and there is no need for it either. With massive MIMO, I think it's fair to say that NOMA makes almost no sense at all. With small dimensional MIMO, you can find cases where it offers like a little bit of marginal improvement. On the other hand, for 5G and beyond, massive MIMO is the physical layer technology that will be used. I think it's fair to say, that no future serious wireless system or standard will not contain massive MIMO as its core technology component. And then, given that you have massive MIMO, there is just simply no need to use NOMA.
So in a way, NOMA is like the poor man's MIMO technology. When you can't afford multiple antennas, then you could utilize this instead to squeeze in more users in a way.
Well, I wouldn't call it the poor man's multiple antenna, because it isn't multiple antenna, right? But put it this way, if you can't afford multiple antennas and you want to do something to improve your system performance, yes, there are definitely cases where NOMA can gain a little bit. Again, I'm from information theory. Long enough blocks and good enough channel state information, then, superposition coding is better than orthogonal access, right?
So if I'm trying to pinpoint why NOMA is not working on top of massive MIMO, is it like in the single antenna case, you said you have 2 users with different signal-to-noise ratios and you transmit to both of them at the same time. Would you, in the multi-antenna case, do you need sort of 2 users with very similar channels except for different SNRs, and then you can add it on top of it, or?
Yeah, in the, say, massive MIMO case, then, with random fading, with very high probability, the users are nearly orthogonal, right? So you can separate them using zero forcing or MMSE beamforming or whatever your favorite linear processing scheme is. And only in the cases really where, let's say you have 2 users with massive MIMO that are in line of sight at the very same angle as seen from the base station, then you'd effectively have a sizer channel to both of them, and you could treat them both then as single antenna. You could treat the channel to both of them as a single antenna channel on which you could use NOMA. So that's true. With some probability, you can find scenarios where the array can't resolve the signals spatially, and when you can't do that, sure, the equivalent system model then would be similar to a single antenna, conventional single antenna system, on top of which you could add NOMA transmission.
I see. So you, in principle or theoretically, you can create scenarios where it works well, but those are not very likely to appear then in practice.
That is exactly the point, yeah.
So, Jet, if you look at the literature on NOMA, what you often see is that they are providing quite convincing performance gains compared to what they call orthogonal multiple access, or OMA. Are these comparisons wrong, or what is it in the research that is not convincing enough for this to work in reality?
It's a good question. I'm not saying the literature is wrong, right? And you definitely can find comparisons where NOMA provides gains. That's not the question. The question is whether those comparisons really relate to scenarios that are of much practical interest. Again, in 5G, we're going to have MIMO and massive MIMO. And then you have to look hard to find a case where NOMA offers any additional gain. The example we just discussed, right, with a large array and line of sight, and then you have two users in the exactly same angle. Definitely. Then again, we're back at the SISO case, and good enough channel state information and long enough blocks, then superposition coding is optimal, and that is power domain NOMA essentially.
Yeah, so I guess then the point is that orthogonal multiple access is not what you want to do in the future. Power domain NOMA is one way of evolving from that, but there are other methods that are more convincing and that are used now in 5G.
You could think of it like that.
So then NOMA could mean other things. I've heard about code domain NOMA. Is that like CDMA or...
To my understanding, it is. It seems to be a... reinvention of CDMA, right? Where you assign spreading codes to users that aren't perfectly orthogonal. And then you're back at an equivalent COM-theoretic model with non-orthogonality.
So CDMA that was used in like 3G, was that based on orthogonal codes, and this would then be non-orthogonal?
Well, CDMA that was used in 3G was based on codes that weren't perfectly orthogonal, but most of the efforts in development of codes for CDMA was to make them as orthogonal as possible. So in that respect, the non-orthogonality in CDMA was like an impairment, right? Then with code domain NOMA, it's more like the goal is to try to exploit that the codes aren't perfectly orthogonal. And in fact, it's not really clear why that would be even a good idea. If you're after the non-orthogonality, well, all right, then assign every terminal the full bandwidth and all the time, and then just let everyone transmit simultaneously and assign them a different channel code, and then you do joint maximum likelihood decoding at the receiver.
So if CDMA was sort of used in 3G and now it's not used in 4G and 5G, do you think it will come back for 6G?
Hardly. Again, CDMA could probably be, again, taken to mean other things than what it originally meant during the 3G development. For example, during random access and grant-free random access especially, then there are now lots of literature and useful methods by which terminals can be assigned non-orthogonal signature sequences or pilot sequences and transmit these at will whenever they have any data to send, and the base station can resolve them relying on sparsity, relying on knowledge of the fact that, well, among these thousands of devices out there who potentially could transmit right now, only a few of them are actually awake. So the coding is subject to a sparsity constraint. Is that CDMA? Well, maybe not according to the conventional methodology, but you could very well call it CDMA. You could call it NOMA. At some point, this becomes like terminology that's being used to sell things that are not what it used to mean originally, I think.
So what else can NOMA mean then?
Well, I think the example I gave, with grant-free random access, where you have terminals that are assigned non-orthogonal signature sequences or codes or pilots, that has been also called NOMA. And that's not strictly speaking wrong in any way. I mean, it is a form of non-orthogonal multiple access, obviously, right? But it's not power domain NOMA. And it is important, I think, to stress upon and understand the distinction between power domain NOMA, which a bulk of the literature on NOMA deals with, and other ways of accessing the channel in a non-orthogonal manner.
Yeah, and if I understood it correctly, the form of NOMA that might eventually make it into 5G would be this type of grant-free access type of methods, when you have a large number of users that want to be just sending a small piece of data, so you can save on the overhead of scheduling them by just letting them operate in this way instead.
Right. And that makes perfect sense. We should add. I mean, while power domain NOMA is questionable at best when you have MIMO or massive MIMO, then non-orthogonal multiple access for short packets during the random access phase in particular is a very powerful technique.
Yeah, and as I've understood, even if we like to measure the highest data rates that you get in your systems, a lot of the users, many of the users are like scrolling through some social media profile, downloads a few kilobit of data, and then and when the bulk of the traffic is a large number of such small requests, it's even if the access scheme is less efficient, if you can get rid of all of the overhead from letting the users connect and schedule them and all these type of things, it will be just faster, less effort for the users to access.
That's right, yeah. Lots of packets are very short and contain only access requests and control information, and that then this type of grant-free access techniques that imply non-orthogonality in the multiple access are definitely very useful and promising.
So if we are ignoring what the name NOMA is normally used for in the literature, is massive MIMO a non-orthogonal multiple access scheme?
Oh, in a way it is, yes, right? Because everyone transmits at the same time. The whole idea with massive MIMO, at least in its canonical form, is that the full bandwidth and the full time dimension is assigned to everyone, so that everyone transmits all the time over the full bandwidth, and then you resolve transmissions through spatial processing. Now, in that spatial processing, if you use a good decoding method like zero forcing, beamforming, or MMSE, or so forth, then you're essentially resolving the non-orthogonality of the transmission and creating interference-free channels, which in addition are very stable. I mean, that's one of the points of massive MIMO, right? You create these wires in the air to the terminals, but you create effective channels that are nearly interference-free, or at least with an interference level that you can have control over. So in that respect, yes, but I wouldn't really want to use the word NOMA, I think, for what we conventionally mean by massive MIMO transmission, where you could say it. Although I'm a little reluctant again to use the terminology for massive MIMO transmission and decoding.
Yeah, I guess that even if you have a purposely orthogonal scheme, it might not be entirely orthogonal reality because of interference from other bands or other systems, and for non-orthogonal is sort of the same. It sort of shows what your ambition is, and maybe the ambition is in massive MIMO is to try to orthogonalize users in space.
Yeah, that's actually a great way of putting it, I think. And, I mean, if you think of it that way, right, there is no such a thing as orthogonal multiple access, because even in classical cellular, you might have orthogonality within a cell. You might partition your time frequency domain and give different chunks to different terminals, but then and you might even have orthogonality among neighboring cells, right? So that we agree in the home cell to use a certain set of time frequency resources, and in the neighboring cell we use a different set of time frequency resources. This is how conventional frequency planning used to work. But at some point, somewhere else, couple of tiers away, there's going to be some cell that has to reuse the same time frequency resources as we had been using in the home cell, and will create interference. And I'm sure you could call that non-orthogonal multiple access. In a way it is, but at least as far as I know, the name NOMA has not been used to refer to that particular scenario. But bottom line is that, well, no transmission in wireless comms is going to be interference free. It's impossible.
So in the recent years, I heard about something called rate splitting, which might be referred to as like the next type of NOMA or the evolved type that might actually be used in practical networks. So what is rate splitting?
So rate splitting is like an evolved form of the NOMA concept, where in principle the idea is that rather than transmitting just a pure superposition of two code words, let's talk about a single antenna downlink channel here with a single antenna transmitter and two terminals receiving. So rather than transmitting just a superposition of two code words that are destined for these two terminals, then the messages intended for the two code words are split into a common part, which is encoded jointly, and a private part, which is encoded separately. And then the transmission consists of this common part plus the two private parts. And then the terminals both decode the common part and their own private part. In principle, that's how it works. And that's rate splitting.
And this is sort of a better method than NOMA?
Yeah, in practical setups, then this offers advantages, yes.
So I've seen your recent paper, Is NOMA Efficient in Multi-Antenna Networks? A Critical Look at Next Generation Multiple Access Techniques, by Bruno Clerks as the first author, and you as one of the many famous authors of this paper. So in this article, which I really recommend for people to read, because it sort of provides you with a comparison between NOMA and maybe massive MIMO, but also with rate splitting, there is a lot of focus on what is called multiplexing gain. What is that?
So multiplexing gain is basically the rate at which the capacity grows when you increase the SNR. So if you think of Shannon's formula, it's like capacity is log of 1 plus SNR, right? And capacity with multiplexing is a constant times the log of 1 plus SNR. And multiplexing gain is a measure of how large is this constant, or more accurately, what is this constant asymptotically when the signal to noise ratio is very large. So think of it that way.
Yeah, no, I brought up this question because I think I often, maybe casually using multiplexing gain as saying that if you serve multiple use in your system, you get the multiplexing gain because you can double your rate. And this is sort of a more formal or strict way of defining this type of gains.
Yeah, you could think of it that way. But it is an asymptotic measure, which has its pros and cons. In a way, I can understand there might be reluctance to use asymptotic measures at all, because, what does it mean that SNR goes to infinity, right? Practical systems might have an SNR of a couple of decibels or something. On the other hand, if a scheme is not good asymptotically, I think it is in general less likely that it would be good at finite SNR. So something being good asymptotically tends to indicate that it's probably technically sound, or probably has potential to be useful also at realistic SNR values.
Yes, and if I understand the premise of this paper, you're showing that rate splitting provides the best multiplexing gain compared to NOMA, for example?
Yeah, there are gains. It provides a higher multiplexing gain than NOMA in the multiple antenna settings.
And sometimes it's also beating conventional massive MIMO or multi-user MIMO methods. Is it an add-on on this technology, or how does it relate to it?
You could think of both NOMA and rate splitting as potential add-ons to MIMO or even to massive MIMO. I think the bottom line is that the more antennas you have, the less this add-on is worth, right? Unless, again, I mean, as we talked earlier here, unless you are in scenarios where the channel degenerates so that all the users are in the same angle as seen from the base station array in line of sight, say, in which case you essentially have an effective single antenna channel to them.
So do you think rate splitting is something that we will be utilizing in future networks to improve the performance further?
Put it this way: if power domain NOMA has any role to play, then it definitely should be replaced by rate splitting, right? But then again, if you have enough antennas in massive MIMO, then the gains are marginal at best, or at least you have to look very hard to find scenarios where it really adds any value. But who knows? There might be future systems where you can only afford small numbers of antennas, and then sure, I mean, these techniques could be useful there. But again, these are niche cases, right?
Yes. So as far as I've understood, if you have a MIMO system, you have multiple single antenna users, and you have multiple antennas at your base station, then you take the minimum of the number of users and of the number of antennas, and this is sort of the maximum multiplexing gain that you could achieve. And then rate splitting cannot really improve upon that number, but it can improve on what you can achieve under more imperfect channel knowledge situation. Is that correct?
Yeah, I mean, this becomes very technical now, but that is in principle as you suggest, yeah.
So I think my only concern from a practical implementation perspective, now we are talking about multiplexing gain information theory, this, as you said, infinitely long codes, and if you're going to transmit a large piece of data, you can spend quite some effort on figuring out what will be your coding rate or modulation scheme and things like that. But if you have users that are transmitting small pieces of data, to sort of involve all of them in selecting all of the users' code. Okay, you have one private part and then you have a common part where you need to put together all of the users. It sounds like you're creating a lot of complications for practical implementations.
You do. I mean, you obviously add complexity, right? On the other hand, I mean, it might be true that most of the packets on the area interface consist or contain rather few information bits. But it might still be the case that the bulk of the bits that are transmitted belong to large packets or long packets. Right? I mean, think of like downloading a huge file or streaming, video. If you can afford some delay with a buffer, then nothing in principle prevents you from putting millions of bits into your code word. And when you enter that regime, right, then with state-of-the-art channel coding, you are at tens of dB from the channel limit, and you probably could afford these more sophisticated techniques also computationally, because there is a long code word, so there are many bits to amortize the computational effort over. So I think for short blocks, questionable, you're right. I mean, the added complexity here might not be worth it. For very long blocks, it's possible.
So then looking into the future, do you think that NOMA or rate splitting have a role to play? Should people invest time in research on these topics?
I think invest time in research, yes, to the extent that questions haven't already been resolved, right? Because these are fields with a huge literature. But I do think there is a value in itself to pin down and solve the foundational information and theoretic problems that we are able to solve, and understand where the fundamental limits are and what techniques are optimal and so forth. For future networks, I'm not so sure. I think, once you have massive MIMO, you probably want to keep things as simple as possible and rely on the spatial, say, processing to separate your users, and the added value of these techniques, NOMA and rate splitting and so forth, is marginal at best, or at least you have to look hard to find niche scenarios where they really add much of performance. There could be cases perhaps with, still systems that we want to build with a single antenna for some reasons. Could be, physical space limitations, for example, or where you can afford only a single antenna or possibly a few antennas. And then, sure, I mean, with time, I think that algorithms that have been developed and that are fundamentally sound eventually will make it to practice. But it isn't obvious. I mean, what use cases or what examples would those systems be?
Information theory in general is an interesting area because many of the things that we are about to utilize today with MIME and also these type of non-orthogonal schemes, people have been talking about this for many decades, but then it's something that comes back with new improved theory over time all the time, and it's really the foundation. So whatever we're going to do, this is sort of what defines the box of things that we could do.
It is, no doubt. I mean, it is a fascinating and also quite difficult field.
Yeah. No, and I guess a related thing here is the interference channel, as it's called as well, when you have like multiple transmitters, multiple users, and they are communicating at the same time and they interfere with each other. So and their things are not entirely known either.
Right. I mean, the capacity region is not known exactly, right? I mean, upper and lower bounds are known, but the exact region, as far as I know, is still an open problem.
Yeah, no, so if you put any of these non-orthogonal schemes that we've been talking about today into a cellular network setting, we might know fairly well how they are behaving within one cell, but then when you have the interfering cells, then there should still be a lot of things to discover how to operate these systems in a good way.
They should.
So is there anything you would like to add before we wrap up?
I think we covered, probably what we could feasibly cover in a session like this. So it might be time for us to approach the close-up here. Is there anything else that you are thinking, Emil, on this topic?
No, nothing that comes to my mind. But if you as a listener have anything that you wonder about on this topic, please feel free to, for example, add a question on our YouTube channel, and we will do our best to either address it in the comment field, or sometimes we are bringing up, as you have seen, special episodes where we're answering questions from the listeners. So with that, thank you for listening to this episode, and see you next time.
Bye-bye.